So here we go. We're going to talk about Newton's second law now. And Newton's second law is the famous force equals ma, or F equals ma equation. What Newton's second law is about is saying that the net force acting on an object is equal to the mass of the object times its acceleration. So let's take an example here. Let's say I have a ball. Let's say I have a bowling ball here. And then let's say I don't have a bowling ball. I don't like bowling balls anymore, so let me just get rid of that. Well, it's not working. So let's say I have, I don't know, whatever this thing is, some kind of object over here. Let's say it's a ball and it's got a mass of 1 kilogram, and it's sitting flat on the floor. It's 1 kilogram in mass, and I want to get this object moving this way, and I'm going to give it an acceleration equal to 1 meter per second squared. So I'm going to have to go from some initial velocity of 0, because it's at rest, to some final velocity in order to get this kind of an acceleration going. And the question is, what force do I need to apply to the ball in order to get it moving? So in order to cause this acceleration, let's just review for a minute. Acceleration is defined as the change in an object's velocity over the change in time to do it. So the change in the velocity is some final velocity minus some initial velocity over delta t. So as long as the initial velocity is 0, as long as you're going to put this ball into motion, you're going to go from 0 to some velocity. You're going to experience, or the ball's going to experience, some kind of an acceleration. So let's say the acceleration you wanted to experience is 1 meter per second squared. In order to get it moving, you have to put some kind of a force on it. You have to apply a force to an object at rest to get it to move. Remember Newton's first law, which dealt with inertia. It's an object at rest wants to stay at rest until some net force acts on the object and gets it rolling or moving. So here's a net force coming in, and we need to apply a net force to this ball to get it to accelerate. Well, according to Newton's second law of motion, the magnitude of the force that you're going to have to apply is going to be equal to the mass times the acceleration. In this case, the mass is going to be 1 kilogram, and our acceleration is going to be 1 meter per second squared. That is going to be, what's 1 times 1? 1 times 1 is 1. Kilograms times meters is kilograms times meters. This is my units. The whole thing now will be divided by second squared. And that will be the net force required to move that 1 kilogram object, get it going at an acceleration of 1 meter per second squared. And this, by definition, is going to be 1 Newton of force. So remember, we talked about the Newton way back when, and we said Newton was a unit of force. At that time, I didn't tell you what the units were to get that and what it really meant. But according to Newton's second law of motion, we calculated the Newton of force is the quantity of force required to accelerate a 1 kilogram mass with an acceleration of 1 meter per second squared. So if you want to know what a Newton is, 1 Newton is the amount of force needed to accelerate a 1 kilogram mass, 1 kilogram object, with an acceleration of 1 meter per second squared. So that's the 1 Newton of force. And the units go kilograms, meters per second squared. So now let's take an example of how we apply Newton's second law. So suppose we have some, let's say here, some object. It's got a mass. Here, its mass is going to be 2.2 kilograms. and I'm going to apply a net force on the object of 1.6 newtons to the right. 1.6 newtons, that's my net force to this object. And the question is, what kind of acceleration is the book going to have? So what is A? What is the acceleration? Well, the net force net, is equal to mass of the object times its acceleration, according to Newton's law. The net force, we said, was 1.6 newtons. The mass is 2.2 kilograms, and we don't know what acceleration is. But if our force is measured in units and our mass is measured in kilograms, then our acceleration will be measured in meters per second squared. That's the way this works out. Because remember, 1 newton is equal to 1 kilogram per meter, kilogram meter per second squared. And that's how the units will work out. So if you have the mass in kilograms, the force in newtons, you're going to get an acceleration in meters per second squared. Okay, so we could say A then will be 1.6 divided by 2.2 meters per second squared, and your book calculates that at 0.73 meters per second squared. And that's how we apply Newton's second law in operation. Now remember, the net force net, is going to be the summation of all our forces when we're doing these kind of problems. One other thing that I want to point out before we close this particular video, and I want to show you, or rather ask the question, if I have an object that's moving, so let's say there's a ball here, it's moving through the air at a, well, let's say it's a cart, and the cart is going to be on some kind of a track, and it's moving at a constant velocity. So let's say the velocity of this cart is a constant, well, let's say it's 5 meters per second, and it's at a constant speed, constant rate, velocity. Then we know that acceleration is equal to 0. Why is acceleration 0? Because the velocity is constant. If there is no change in velocity, then acceleration is 0, because acceleration is delta v over delta t. So if there's no change in velocity, it's just going at a constant velocity, the acceleration must be 0. If that's the case, my question is this: does that mean that there are no forces acting on this cart? I'll say it again. If the cart's moving at a constant velocity, does that mean that there's no forces acting on the cart? And the answer is no, of course not. All it means is that the net force, why is this not working now? The net force is 0 because there is no acceleration. Acceleration is 0 in this case because we're moving at a constant velocity. So if the acceleration is 0, we know that the net force is 0. But there still could be forces acting on the cart. Maybe there's somebody pushing the cart this way, and the cart is in motion now. So let's remember, the cart is moving this way at 5 meters per second. Let's say someone's running here, and they're running, pushing this cart with a force of, well, let's say 20 newtons. And there's someone over here trying to stop the cart, running backward, as it were, pushing this way on the cart at 20 newtons, then the cart could still be moving in that direction at a constant speed, because the net force is going to be 0. So the net force can be 0, but individual forces acting on the cart need not be 0. Need not be. Something is wrong with the pen today. Need not be 0. Okay, so that's something to think about.